Hello, good afternoon, and welcome to this AHDB webinar. My name's Scott Raffle. I work for the AHDB, and I shall be your chair for this afternoon's session. This week, AHDB is running a Carbon Awareness Week, and the purpose of this is to raise awareness in agriculture and horticulture of carbon emissions and what you as farmers and growers can actually do about this. So today's webinar is entitled Understanding Fertilizers, Carbon Emissions and What You Can Do to Reduce Them, focus being very much on fertilizers today and how to manage them to the benefit of us all. So a few housekeeping issues this morning. You are the attendees, you are muted, so you can see and hear us, but we can't hear you. You will have the opportunity to ask us some questions, and there is a little mock-up on the screen here on the right-hand side. That's a mock-up of your control panel, and you will see halfway down that panel, there's a little grey bar and it says questions. So during this afternoon's event, you can click on that. If you have any questions during the presentations or at the end, you can submit a question via that facility. We will be dealing with questions after each presentation, and I shall deal with those when we get to them. The next thing to say is that today's event is being recorded, so it's a live webinar, but it's been recorded. So for those of you who wish to watch it again, you will be able to do so, and anybody that hasn't had time to join us today will also be able to view it. It will be uploaded to our AHDB website, and hopefully that will be available within a week of today's live event. For those of you that want basis, dairy or pig growth points, you can submit your details. There is potential for you to do so by sending them to Naya Katri at that email address that you'll see at the bottom of the screen. So that's naya.katri@ahdb.org.uk. So to business, we shall move now into the webinar program, and just to explain what's to come this morning, or this afternoon, I should say. We have two speakers, both from ADAS, both specialists. Christina Baxter is going to kick off, and she's going to tell us about on-farm carbon footprint and what's contributing, and so the contribution of nitrogen fertilizers to carbon emissions. We'll deal with questions, and then Anne Bhogal, Christina's colleague from ADAS, will deal with nutrient management planning. We've also got the benefit today of another specialist, Tim Kerr, who works for Hutchinsons, who is our fertilizer specialist, who's been working in the industry for many years, and Tim is here really just to put some of the information into context for you, the farmers and the growers. Now, in terms of the timing of this afternoon's event, we are planning to run till about 1 o'clock. It might overrun slightly if we've got lots of questions and discussion to take. Christina will run for about 20 minutes, and there'll be about 5 minutes for questions and discussion. And then similarly, Anne will be about 20 to 25 minutes, and we'll take more questions and discussion at that point. So first up is Christina Baxter. Christina is a crop research consultant at ADAS. She specialises in applied research with the main objective of sustainably increasing crop performance on UK farms. Now, within her role at ADAS, Christina has led farmer-centric research through the YEN networks, and she's also involved in better understanding carbon footprinting on farms and mitigation strategies, which can help us to achieve the net zero target. Christina, good afternoon. The floor is yours.
Great, thank you very much, Scott, and hopefully everybody can see my screen and hear me okay. I just want to start by saying thank you for inviting us to talk at today's AHDB second session in your Carbon Week event. And Anne and I are going to be talking about how we can reduce our on-farm carbon footprints, specifically through maximising our fertiliser use efficiency. So as Scott's alluded to already, we're going to split the session into two sections, where I'll first talk about how we calculate carbon footprints and how the emission hotspots differ between different farming systems. And this will be a little bit of a revision of Sarah Wynn's session yesterday for those of you that attended. I'll then go on to talk about specifically nitrogen fertilizers and the contribution that the manufacture and application of nitrogen fertilizers, both in terms of synthetic form and organic materials, have on our carbon footprints, and then how we might be able to reduce the portion of nitrogen fertilizers on our carbon footprints. And then in the second session, Anne's going to talk about nutrient management planning and specifically fertilizer use efficiency. So Anne will go on to discuss crop requirement, what nutrients are provided by our soils and also by our organic fertilizers. And then Anne will also talk about emissions associated with organic fertilizer application and how we can minimize these and the benefits that these materials have on our soil organic matter content and our carbon storage potential. So before I jump into talking about the contribution that nitrogen fertilizers have on our carbon footprints, I thought it would be good to go over how we calculate carbon footprints. And essentially, an on-farm carbon footprint is the total greenhouse gas emissions emitted by the different activities that are associated with agricultural production. So to calculate the greenhouse gas emissions for a specific on-farm activity, we multiply the information around that activity, and this could be amount of fuel used or amount of fertilizer applied. We multiply this by an emission factor. An emission factor is essentially a coefficient which allows us to convert this activity information and quantify it in terms of the amount of greenhouse gases emitted. And then depending on what greenhouse gas in particular is associated with that activity, we then multiply it by a global warming potential in order to quantify the emissions in terms of kilograms of CO2 equivalent. And this is the main form of unit that we use when we calculate carbon footprints. And the global warming potential is the heat absorbed by a particular greenhouse gas as a multiple of the same amount of heat that would be absorbed by the same mass of carbon dioxide. So the global warming potential of carbon dioxide is 1, whereas the global warming potential of nitrous oxide is 300. And this means that nitrous oxide is 300 times more potent in terms of its global warming potential compared to carbon dioxide. And there are a number of different calculators that you can use to measure your on-farm carbon footprint, and these are freely available online. And I know they'll be discussed in more detail in other Carbon Week sessions. And also it's a measure that we're in the process of integrating into the yield enhancement network through Yen Zero. So when looking at the whole farm system, there's quite a wide range of sources that are emitting greenhouse gases that need to be considered. For example, in a livestock scenario, we have N2O emissions from grazing, also from housing of livestock and manure management, and also a lot of emissions originating from methane from enteric fermentation. In horticultural scenarios, we have common sources of emissions of N2O emissions from composting and also carbon dioxide associated with the electricity and irrigation of controlled environment growing systems. And there's also embedded emissions to consider from your inputs such as feed and fertilizer and agrochemicals. But an important point to note when talking about farm carbon footprints is that agriculture is one of the few industries that has the ability to act as a carbon sink as well as a carbon source. So carbon can be sequestered in actively growing trees or hedges, and also carbon can be sequestered in the soil through inputs such as organic amendments, and Anne's going to talk about that in a bit more detail. And also there's a consideration of changing management practices which can help that carbon sequestration in the soil, such as reduced tillage. So when considering the carbon footprint specifically for a combinable cropping scenario and the carbon footprints that we see for the different activities associated with crop production, common figures that we see for these activities in terms of on a per hectare unit basis are around 100 kilograms of CO2 equivalent per hectare for the inputs of seed, ag chemicals, non-nitrogen fertilizers. We see around 200 kilograms of CO2 equivalent per hectare for both grain drying and liming applications, and around 400 kilograms of CO2 for machinery fuel use. But the main contribution is the emissions associated with the manufacture of nitrogen fertilizers and the N2O soil emissions associated with that application of those fertilizers and organic materials. And with these two factors combined, they can contribute up to 2/3 or even more of the total carbon footprint in terms of crop production. And it's worth mentioning that depending on what type of system you're considering, these figures can change. So, for example, a system which uses a reduced tillage regime will have lower emissions associated with fuel use compared to a ploughed situation. And also a scenario which predominantly uses organic materials will have lower embedded emissions associated with the manufacture of nitrogen fertilizers. And also, depending on what farming system you're looking at, these hotspots can change. For example, a potato production will have high emissions associated with fuel use because of that requirement for soil movement and crop storage. Also, for a dairy system, high emissions are associated with embedded in feed, manure management, and also enteric fermentation as well of livestock. So this slide just shows a really simple comparison of the types of activities that are contributing to the carbon footprint for different farm outputs of a feed wheat crop and an extensive suckler beef scenario. So in the feed wheat scenario, you have a lot of the main contributions are coming from the manufacture of nitrogen fertilizers and the soil emissions from the application of those fertilizers. So this is the dark blue and the light blue sections of the pie chart. Whereas in extensive suckler beef, you've got big contributions coming from enteric emissions and feed embedding. So this is the brown and the turquoise sections, but also around a quarter of the contribution is coming from manure management as well. And we've measured the greenhouse gas intensities of cereal yen crops, which were entered into the competition between 2013 and 2019. And this is shown in the graph here, where we've measured greenhouse gas intensities in terms of kilograms of CO2 on a per tonne output basis. So in the graph here, you've got greenhouse gas intensity on the left y-axis, and you've got yield on the right y-axis, which is these yellow dots. And then the greenhouse gas intensities are split into the different activities of operations, inputs such as seed, non-nitrogen fertilizer and ag chemicals, and also nitrogen fertilizer manufacture and N2O emissions. And the graph here is organized from low to high N2O emissions. And what this data has shown us is that a huge amount of the carbon footprint is contributed by these emissions of nitrogen fertilizer manufacture and soil N2O emissions on the back of those applications of those fertilizers. But also what the data has shown is there's a slight negative relationship, which is showing that high yielding crops tend to be associated with lower carbon footprints when we measure the carbon footprint on a per tonne of output basis. And this is one of the 4 pillars of the NFU, is increasing our productivity without increasing our inputs, and this can help us to achieve net zero. So now we have a better idea of how the manufacture of nitrogen fertilizers and their application contribute to our farm carbon footprints. And I want to delve a little bit deeper into where these emissions are derived from. And the manufacture of nitrogen fertilizers is an energy intensive process which involves the reaction of atmospheric nitrogen with hydrogen. And the energy requirement tends to come from sourcing the hydrogen component, which is commonly sourced from natural gas. But fertilizer manufacturing in the UK and EU have cut their emissions since 2010, and they've cut them substantially using investments in abatement technology in the manufacture plants. And this abatement technology scrubs the N2O emissions on site. And this has resulted in emissions reducing from over 7 kilograms of CO2 equivalent per kilogram of nitrogen to nearly half that, at 3.5 kilograms of CO2 equivalent per kilogram of N. And on the graph on the right there, it shows the contribution of this reduction in manufacture emissions to the greenhouse gas intensity of wheat crops on a per tonne of output basis between 2009 and 2019. And we also hope in the near future that we'll see the emissions associated with manufacture reduce even more so, with companies like Yara investing in technology which involves the production of hydrogen using the electrolysis of water and using renewable energy to do that. But with that being said, not all regions of the world use the same technology to produce nitrogen fertilizers, and this means that the emissions associated with fertilizer manufacture will change depending on the region of origin. So European nitrogen fertilizer manufacture emissions can be up to 3 times lower than those, for example, produced in China. And in the two graphs here, we've got the carbon footprint of different nitrogen products. On the left, you've got ammonium nitrate products, and on the right, you've got urea products. And it's showing the big range in carbon footprint for these nitrogen fertilizers, where European products tend to be on the lower side of the carbon footprint, whereas Chinese originating fertilizers are showing quite a big peak in carbon footprint. And this means that when you're sourcing your fertilizer for your farming systems, it's important to consider the region of origin and also ask your suppliers for abated fertilizer. And this allows you to help minimize the carbon footprint associated with the manufacture of synthetic fertilizers. So moving on to emissions associated with the application of these fertilizers and organic materials, these are derived by direct soil N2O emissions and indirect emissions associated with the leaching and volatilization. And within the UK, we've recently changed the way we calculate the direct soil N2O emissions associated with synthetic nitrogen fertilizers. And this was on the back of UK field studies, which were undertaken through the Minnow project, which was led by ADAS, which showed that emissions in dry areas of the UK, such as the Arable East, tended to be lower than the IPCC default, which is that 1% of the nitrogen applied is lost through direct emissions. But with that being said, these emissions were shown to be higher in these studies in wetter regions of the UK, such as in the West. So on the back of this, we've recently revised the calculation associated with these direct emissions within the UK national inventory. And in terms of emissions associated with ammonium nitrate fertilizer application, these are now scaled to take into account annual rainfall. So in a scenario where you're applying 200 kilograms of N in the form of ammonium nitrate in an area which receives around 600 mil of rainfall, your emissions will be around 0.6 tons of CO2 per hectare. But when you increase that rainfall twofold, your emissions will increase on the back of this to 1.7 tons of CO2 equivalent per hectare. But in terms of urea, the annual rainfall isn't taken into account, so it tends to have lower direct emissions, but urea does have higher indirect emissions associated with volatilization. So in the same scenario of applying 200 kilograms of N in the form of urea, you'll have around 0.7 tons of CO2 equivalent per hectare, whatever the rainfall received. And looking at indirect emissions associated with nitrogen applications, we use a standard IPCC value for quantifying the amount of material leached into the environment. And this value is 30% under cropping scenarios, but for grassland scenarios, values are modelled to consider elements such as soil and climate. Also, crop residues can contribute a significant proportion of your indirect emissions, which is directly proportional to yield. For example, a wheat crop, which has a harvest index of around 50% and a yield of around 8 tons per hectare, has associated emissions of around 0.35 tons of CO2 per hectare. And this is taking into account both below ground and above ground biomass. But because of the high carbon nitrogen ratio of straw, it means that the N2O emissions are unlikely in reality, at least in the short term. So consequently, growers that are achieving high yielding crops and they're not removing their crop residues from the field tend to be being penalised by these calculations, and it tends to incentivise straw removal where growers want to reduce their carbon footprints. But we do know that incorporation of straw can help to improve soil carbon and soil health, and I think Anne's going to tackle this issue a bit more later on. So how can we reduce our emissions associated with nitrogen application? Well, this is predominantly through improving our nitrogen use efficiency, so by focusing on our crop and our soil. So this means being cautious of your predicted yield, so considering the season you're in and the potential limitations of that season, knowing how much nutrient is being provided by the soil, and Anne will talk about that in a bit more detail. Soil structure is also important, particularly good aeration will help improve your nitrogen use efficiency, and not applying in waterlogged soils where you've got these anaerobic conditions. Inhibitors are also a way we can help reduce N2O emissions, and I'll talk about that in a bit more detail in the next slide. But finally, an important point is going back to this productivity, and increasing yields with the same or fewer inputs will have a knock-on effect, a positive knock-on effect on reducing your carbon footprint. So nitrification inhibitors are a tool in our toolbox which we can use to help reduce our N2O emissions associated with the application of both synthetic and organic nitrogen fertilizers. And nitrification inhibitors slow the rate of conversion of ammonium to nitrate. And example chemicals that are associated with nitrification inhibitors are DCD and DMPP. And DEFRA funded UK research, which ADAS were involved with, that showed the effectiveness of these nitrification inhibitors in reducing N2O emissions. And in this work, DCD was trialled in both arable and grassland scenarios. And one of the take-homes from this work is that we do tend to see quite a considerable variation in N2O reduction efficiencies. And you can see the range there is very big. But on average, through this trial work, DCD was effective in reducing N2O emissions, particularly in arable scenarios. They saw an 80% reduction in N2O emissions, whereas in grassland scenarios they were less effective, but you're still achieving around a 60% reduction in N2O. And this variation was predominantly down to temperature, soil clay content, and also organic matter content of the soil as well. But an important point to make when discussing nitrification inhibitors is that we don't see an agronomic benefit of these products. So nitrification inhibitors haven't been seen to improve yield, total N offtake, or nitrogen use efficiency. So when considering how we roll out these nitrification inhibitors on a wide scale to help reduce our N2O emissions and therefore our carbon footprint associated with agricultural production, there's likely going to need to be incentives there in order to roll these out on a wide basis. But they are a tool in the toolbox which we can move on to help reduce our N2O emissions. So that's me on the first section. I'm happy to take any questions. I think we've got a few minutes to do so.
Thank you very much indeed, Christina. That's very comprehensive. Can I bring Tim Kerr in at this stage as well? Tim's joining us. Tim is a fertilizer specialist who's been working for more than 20 years. He currently works for Hutchinsons. He's a facts trained, and he examines facts courses as well. Tim, before we get into specific questions for Christina, just I suppose getting your experience and context on this, how easy is it for growers to accurately calculate their carbon emissions on farms these days? Christina mentioned the use of various models and calculators. How in practice, how easy is it?
It's becoming more the ease at which people can do that is improving. I think the more people are engaging in these kits that can monitor their carbon footprint. But I think Christina hit the nail on the head when she referred to the fact that nitrogen fertilizer invariably is the largest contributor to the carbon footprint, and improving the management of nitrogen and increasing nitrogen use efficiency is invariably the area that farmers can focus on to reduce their carbon footprint.
Okay. Have you got any other specific questions before I start taking others?
Well, one thing I think we should possibly consider is that within the nitrogen use efficiency, you're looking at improving soil management and the wetter areas that Christina was referring to, having the higher N2O emissions, I think there are lessons that we can learn there in improving our soil management of the wetter areas to reduce nitrous oxide emissions. So yeah, that would just be a comment.
Okay, thank you. First, there's a number of series of questions I've got here. First question for Christina is, does grass growth contribute to carbon sequestration?
In terms of grassland scenarios, your carbon sequestration will be improved versus a cropping scenario where you tend to have more soil management. So these carbon calculators will have better soil carbon sequestration on a grassland scenario versus a cropping scenario. And if you change the land use, that will have a big impact. If you go from grassland to arable, that will have a big impact on your carbon footprint as well.
Okay, thank you. Another one regarding some of the research you mentioned. Did ADAS do any research looking at the N2O emissions from nitrogen application of urease inhibitors?
We are working on urease inhibitors at the moment. So we are undertaking some trials currently, and we have done in recent seasons as well. So I think that's hopefully work we will be able to present in hopefully at the end of this season.
One point on that, Scott, is that urease inhibitors are designed to reduce ammonia volatilization. So ammonia volatilization is not a greenhouse. Ammonia is not a greenhouse gas. It obviously there's an impact in the Clean Air Act, but urease inhibitors might have an indirect effect on the carbon footprint, but that's not their prime function.
Okay, well, there's a related question also. Somebody saying, are urea plus inhibitors in the West better than ammonium nitrate? Or AN, sorry, I should say. Christina, do you want to deal with that, or do you understand the question?
I don't understand the question.
Yeah, no. I'm not quite sure I understand that either. Perhaps we can take that up later on with the questioner. Another question here, how does leached nitrogen contribute to carbon emissions?
So they are considered in your carbon footprint, the leached fraction of the nitrogen material. And that's, as I mentioned, in a cropping scenario, around 30% of the nitrogen applied is considered within the carbon footprint as leached, but it's slightly different in a grassland scenario because there's a bit more going on in terms of understanding and quantifying the amount of leached fraction, but it is considered in the carbon footprint. Okay,
this next question is perhaps well, let's put this to Tim. Do you think agriculture should strive to be net negative rather than net zero?
Well, I think we should aspire to be efficient in production and manage our inputs as best we can in order to produce the amount of food that we need to produce to feed everyone. So the answer to that is it would be very, yeah, obviously it would be lovely to say that we're a negative in terms of carbon footprint, but realistically there's a role in food production as well, and I think we have to balance the role in food production with managing the environment and reducing our carbon footprint accordingly.
Yeah, okay. Next one, I'll put this to Christina. Are the benefits in liquid fertilizer application significant for the carbon cycle?
Are the benefits in liquid application significant for the carbon cycle? I think with the solid versus liquid is that you're still applying the nitrogen fertilizer, so you still have those emissions associated with both the manufacture and the application. So I'm not aware of big differences between liquid and solid in terms of your carbon footprint.
Okay.
Just a very quick comment on that. One of the key aspects of improving nitrogen use efficiency is accuracy. We spend a lot of time in producing nutrient management plans, but delivering those accurately is one of the fundamentals to getting improved nitrogen use efficiency. And if liquid fertilizer can offer a more accurate application method, then it can have a role.
Yeah, okay. Yeah, that's right.
Thank you. There's a comment here. Presumably, if the government does introduce various new carbon taxes, this could have a big effect on the relative prices of different nitrogen sources around the world. But would the government really apply new taxes on UK food production? I don't know if anybody has a comment on that. Either of you want to comment on that?
It's a good comment to make that we should be incentivising farmers to buy their fertiliser from EU origins because of that reduction in the carbon footprint.
Okay. I like this next question. This is very helpful. The figures show that there can be a massive reduction in emissions by switching the source of fertiliser. Is this actually taken into account in the calculators that we use?
It depends which calculator you're using. So some calculators are more specific. They allow the user to input more detail about their fertilizers. So for example, the Cool Farm tool, you can give information about where, in terms of the origin of the fertilizer and also the year of manufacture as well. But that being said, some farmers might not know that information, but it's good to get that information from your supplier when using your calculators, that you can then quantify the emissions associated with manufacture in more detail. So then you can apply those reductions associated with when you gain your fertilizer from areas such as the EU versus other regions of the world.
Okay, we're getting lots of questions about carbon calculators here. So I think probably I'm just conscious of time. I think probably we'll try and take some of these up after the event. I can confirm to all of those who have submitted questions on this subject that Christina has very happily agreed to reply to you separately if we don't have time to deal with them. Just one more comment I'm going to raise here. Somebody's put, retaining ammonium in the soil will inevitably contribute to ammonia emissions. Government is keen to reduce ammonia as well. Probably not the best solution is the comment here. I don't know if you've got anything else to say on that, either of you.
Well, ammonia is part of the nitrogen cycle naturally, that ammonia will mineralize to nitrate, and crops will utilize nitrate and to a lesser extent ammonium, but you won't eliminate ammonium from the soil because it's part of the natural nitrogen cycle. So if it's a reference to the nitrification inhibitors, then the purpose of those is to slow down the breakdown of ammonium to nitrate to reduce the risk of leaching when you get high levels of nitrate in the soil. So I mean, they do have a function, and they can be effective, but yeah, I don't think you can't get rid of ammonium from the soil.
Okay. Well, Tim, Christina, for just now, thank you to you both very much indeed. We must move on in the interest of time. I should just say we've had one or two questions about can people see the presentations later on. As I said at the start, this recording will be made available on our website. We can, if people specifically want to receive the slides separately, we can try and look into that for you and try and see what we can do. So we will move on at this stage. Thank you, Tim. Thank you, Christina. I'm going to introduce our second speaker now, who is Anne Bhogal. She is a principal soil scientist in ADAS, involved in research and development of policies on soil and nutrient management. Anne has a particular interest in the impact of organic amendments and cover cropping on soil quality, carbon storage and nutrient cycling. So she's going to take us through the next phase of this presentation this afternoon, the actual nutrient management planning itself. Anne.
Thank you very much, Scott. I'll just make sure you can see my screen. Hopefully you can see it now. So yeah, thank you. Good afternoon, everyone. I'm just going to really now pick up from where Christina left off and deal in more detail about nutrient management planning and how that can help us reduce emissions on farm. So this first slide basically shows you the key steps to a nutrient management plan. I could probably give a talk on each of these steps. So I'm going to try and rattle through them and just give you the salient points in relation to how these different steps will help reduce emissions. So First and foremost, you need to understand what your crop needs. Then look at what is supplied for free in the soil. If you're using manures, account for the nutrients supplied by those manures. And then and only then can you work out how much manufactured fertilizer you need to bring in to top up those needs. And then once you've done that, it's really important that both manures and fertilizers are spread accurately, evenly, and in a timely way so that you actually minimize losses and maximize the nutrient use efficiency. So firstly, what does a crop need? Well, Christina's outlined already that what we want to do is try and enhance crop productivity whilst minimizing our inputs. And it's really important to use a fertilizer recommendation system to understand what the crop needs at the outset and adjust that where appropriate according to your expected yield, with a knowledge of what the season's like and past performance of the field in question. And obviously the amount required will depend on what you're growing, when you drilled it, and your soil type, amongst other things. So once you've understood what your crop needs, it's then what have you got in your soil? What can you get for free? So for nitrogen, it's all about understanding your soil end supply. And there's standard values within RB209 based on your soil type, your previous cropping and your rainfall. But also you can measure it ahead of working out your fertilizer recommendations. And this is particularly useful if you are in a season where you might have high N residues. For example, if you regularly use organic materials, or you've had a high N residue crop, or perhaps the winter was particularly dry. But it's not only nitrogen you need to consider. Yes, the carbon footprint of nitrogen fertilizers is the key one that we're trying to reduce here. But obviously, if you don't get your other nutrients in optimal supply, so your phosphorus, your potassium, your magnesium, sulfur, pH of the soil is correct, that nitrogen won't be used effectively and efficiently. So every 3 to 5 years, you need to sample the soil, and this requirement fits with the farming rules for water. Analysing for pKmg and pH, so targeting pHs of 6 and 6.5, depending on what you're growing, and targeting indexes of 2. And this chart over on the right-hand side just shows you how grain yields change in relation to your soil P status. So wheat in blue and red for barley. You can see that as your soil P status increases to about index 2, so that's 16 to 25 milligrams per litre in your soil, you can see that the crop yield responds, but then it flattens off and you see no further increases. And in fact, as your soil P status increases further, so if you get up to index 4 or 5, so over 60 milligrams per litre, you start to see some potential environmental emissions of phosphorus, particularly in the runoff. So once you know what your crop needs, you know what your soil is going to supply, it's then you need to consider what organic materials you are using. And I would say that actually having an integrated nutrient management plan, one that involves both organic manures and bag fertilizers, is really beneficial for a number of reasons. Here you can just see that actually by using organic materials you can replace a significant proportion of your bag fertilizer requirements. So for example, application of pig FYM at typical application rates supplies a modest amount of crop available nitrogen, but is a good source of phosphate and potash and can replace about 200 pounds per hectare in terms of fertilizer replacement value. I'm hoping you can still see my screen. Sorry, I've just flicked something. Just put it back onto, there we go. Yeah, and something like biosolids, that's a good phosphate source, whereas something like whole digestate is good for supplying nitrogen. So it's important that you understand what you're applying and how much you're applying, and therefore what nutrients are being supplied. So knowing the nutrient content of a manure is key. And there again are some typical values within RB209 that you can use. But new manures are inherently variable, obviously depending on the livestock, but also the diet and the storage of those materials. So a laboratory analysis is also really useful, analysing for the key nutrients and available nitrogen, ammonium N, uric acid N in terms of poultry manures. And for slurries, you can use N meters or hydrometers, working out the nitrogen content based on the dry matter content. And it's not only the total nutrient content that you need to understand, it's the crop available nutrient content. That is what is going to replace your bag fertilizer. So for example, for nitrogen, you need to understand firstly what's in the manure in terms of the readily available N content. So that's your ammonium N, your nitrate, your uric acid N for poultry manures. Then a proportion of the organic N will mineralise during the season and become crop available. And then you will also, once you've applied those materials, you will inevitably get some losses via leaching, volatilisation, denitrification, and really want to try and minimise those losses, but also understand what they will be, because then that determines what is crop available and therefore can be used to replace fertilizer. And again, RB209 has some standard values for this and some guidance depending on when you apply the manures. But you can also make it more specific to your farm by using the manna model, which will predict crop available nitrogen and phosphate and potassium. And manna is basically embedded within the Planet software. But as I said, it's not only nitrogen, it's important that other nutrients are in optimum supply so that you can reduce, so you can get a crop growing well and reduce the need for bag fertilizer. So for phosphate and potash, if your soil index is low, we use available phosphate, so we assume 60% availability for phosphate and 90% availability for potash. If your soil is at index 2 or above, we tend to use total figures of their availability, because you're just applying a maintenance dressing in these cases. But also remember that manures supply valuable amounts of sulfur too. And this table that I show on the right is basically just lifted from RB209 and shows that sulfur availability will vary with your type of manure and when you apply it. So it's important that you take into account the other nutrients, and this can then reduce the fertilizer supply of these as well. So once you've worked out how much manures are going to supply, it's important that you maximise that supply by spreading them accurately, evenly, and in a timely way. So quantify the application rates, know your spreader loads and the discharge rates, the spreading width and how fast your tractor's going. For slurries and liquid manures, use band spreaders because they can give accurate application rates across known bout widths, and they also minimise ammonia volatilisation losses. And then in terms of timing, certainly on light soils, spring applications of these materials is preferable. This chart just shows the effect of application timing on a light soil, particularly for manures with a high readily available N content, so slurries and poultry manures. Leaching losses from September, October, November applications can be significant. Less so for solid manures, farmyard manures. And this data here really supports the nitrate vulnerable zones closed period rules. On heavy soils that are drained, the situation is a little bit more complex. because actually applications to drain soils in springs can be a bit risky, particularly where you have a low soil moisture deficit and it is a wet spring. So this chart just shows an example of this, where an application in early spring to a wet soil resulted in a peak in phosphate concentrations in the drainage waters following that application. So increase in phosphate, sediment and ammonium N losses associated with that application compared to if it had been applied in the dry autumn. And you can just see the impact of this just by looking at the colour of the drainage waters coming out. So on heavy soils which are drained, autumn applications may be more preferable in terms of minimising losses. So we've worked out what our crop requires, what's in the soil, what our manure applications are going to give us. Then and only then do we need to top up with fertiliser, bag fertiliser. And as with manures, in order to maximise the efficiency of their use, it's important that they're spread accurately, evenly and in a timely manner to match crop demands. And most fields will receive a uniform rate of fertiliser. But there's often large intra-field variability due to soil type or topography. And actually by using precision application, so variable rate application, we can again reduce the need for fertilisers and improve the carbon footprint. So the map on the right just is a canopy scan basically of a field, looking the NDVI reflectance values with red and brown areas sort of signifying very low or no crop cover, green and blue indicating high crop cover. And so you can see if you apply a flat rate of fertiliser across that field, it's not going to be used particularly efficiently, certainly where there is no crop present. Likewise for soil testing, you can do soil mapping. So the bottom chart is basically a soil map of phosphate concentrations. Down at the bottom in the orange, you've got a soil at index 1, going all the way up to index 4. So again, if you applied a flat rate of fertiliser across that whole field, it's not going to be utilised particularly well as a whole. You're going to not have enough in one area or too much in another. So satellite positioning and guidance and variable fertiliser rates can reduce the fertiliser need and increase that efficiency. So that's really all I wanted to say about nutrient management planning. As I say, a bit of a whistle-stop guide through. As I said earlier, having an integrated management plan which involves manures and fertilisers is beneficial, not just because you're replacing nutrients by having organic materials on farm, but also you're applying organic matter, you're returning organic matter to the soil. And as you can see here, here's some examples of the amount of organic matter that you can return from a typical application of bulky organic materials, so the solid organic materials, anywhere between 2.5 to 5.5 tons of organic matter returned per year, depending on your application rate, which is obviously controlled by how much nutrients there are in those different manures. For something like a slurry or liquid manure, obviously much lower dry matter content, so less carbon is being returned. So anywhere between 1.5 tonnes per hectare per year from a slurry application. So obviously these materials are returning carbon back into the soil. And some years ago, we did some work for DEFRA. I've skipped ahead of myself, so I just wanted to show how soil organic matter levels change as a result of applying organic materials. This is some work we did for RAP, looking at a number of long-term experimental sites applying different manures. for a number of years. So we're looking here at the percentage change in topsoil organic matter content. And I just want to draw your attention to the two big bars. So the green compost applied for 9 years, supplying 50 tonnes of organic matter, and the FYM applied for 20 years, supplying 90 tonnes of organic matter per hectare. And you can see that the percentage change was exactly the same. So about 25% increase in topsoil organic matter from these materials. So the green compost resulted in a much quicker increase in organic matter compared to the farmyard manure. And that's down to the stability of the different materials, the decomposability once they're in the soil, and how long, therefore, they will stick around. So green compost is much more stable compared to farmyard manure, which turns over more rapidly. And what I was going to say was we did some work some time ago with Defra and David Paulson at Rothamsted to try and come up with some numbers of the potential carbon storage that would result from these kinds of applications. And so here's just some average numbers that we obtained from UK experiments looking at this. And so, as you can see, farmyard manure, around 20 to 25% of the carbon that you return to the soil is retained over the long term, compared to digested biosolids or green compost, which is much more stable, up to 50% is retained. And we equated that through to the potential carbon increase. So anywhere between 600 and 1,500 kilograms per hectare per year carbon increase. If you look at that in relation to what's already in the soil, you can see that actually it's quite a small percentage of your carbon stock that's already in your soil, so 0.7 to 1.5. So actually it's quite difficult to detect those increases on a yearly basis because it's very small in relation to what's already there. I've put in also some figures for cereal straw for a typical a return of cereal straw from 7.5 tonnes of straw going back. You can see that the retention of cereal straw is much lower, so 10 to 15% of the carbon returned is retained. But we do see, so cereal straw will, over the long term, increase soil organic matter levels, albeit to a small degree. But I know that there's a webinar later on in the week on soil carbon sequestration, and I just, and they'll probably go into this in much more detail. I think David Paulson is speaking at it. But I just wanted to put some caveats to the use of certainly organic materials and accounting for soil carbon sequestration. First of all, some of the estimates, as I say, I haven't put errors on those numbers that I show you. They're quite variable and they depend on what soil depth was measured in the study. But that to one side, there are some limitations to thinking about soil carbon sequestration in your carbon accounting. Obviously, soils have a finite capacity to store carbon. A typical long-term arable soil or grassland soil will have an equilibrium level of carbon in it. And it's only when you change practice that that carbon level might increase or decrease depending on what you're doing. So carbon levels will move from one equilibrium level to another over a period of about 20 to 30 years. And obviously, if you stop doing that practice, it's reversible, so you can undo the good that you've done. There's obviously potential for pollution swapping, so you do need to think about what other implications are associated with that increased carbon sequestration. And I suppose the one for farm manures and organic material use is, what is the alternative fate of those materials? Aren't we already achieving this? So most organic materials are already accounted for somewhere because they're already applied to a soil. And then finally, can we reliably measure and verify those changes? As you can see, it's a very small percentage of your stock that's already in your soil. So actually detecting the difference is quite difficult to do. And so carbon sequestration is currently within some of the carbon calculators, but I would say our understanding of it is not quite there yet, and some of the estimates are perhaps not as robust as something from, say, for example, looking at bag fertilizer emissions. Having said that, I would say that actually putting the carbon storage aspect to one side, that using organic materials will help reduce your carbon footprint in other ways, in that they improve soil health. So if they improve soil structure, water holding capacity, those kind of things, they will improve the ability of the crop to root, to capture nutrients, to water, and to use therefore nutrients more effectively and efficiently, so that you don't have to apply so much bag fertilizer. But not only on the sort of climate change mitigation side, using organic materials and the benefits they have to soil health by reducing runoff and erosion and waterlogging will help a soil become more resilient to the effects of climate change. So we're predicted to have more extreme events. We've been having more extreme events. If our soils are able to cope better with those because we're improving organic matter levels, then that is another benefit alongside the sort of mitigation, the carbon capture side of things. So I've come to the end really of what I wanted to say, and I really put this summary up to really go through what both Christina and I have hopefully covered this afternoon. Yes, manures and fertilisers contribute a large proportion of a farm's carbon footprint, but there are ways in which we can reduce this and increase the efficiency of the use by, as Christina says, sourcing abated fertilisers and knowing where they've come from, using nitrification inhibitors, using a nutrient management plan and increasing the efficiency of nutrient use, using variable rate application technologies, and integrating manures and fertilisers so we have those multiple benefits. We close those nutrient cycles and organic matter cycles. We reduce manufactured fertiliser and we increase the resilience of our soils to mitigate and adapt to climate change. And that's all I wanted to say. Thank you very much, Scott.
Thank you so much, Christina, for your practical guidance and help to all farmers and growers out there. Perhaps I can bring our specialists back in, Christina and Anne, if you can stay with us. First of all, I would just say Anne made reference to the AHDB Nutrient Guide RB209 on several occasions in her presentation. That is available. We hope that most farmers and growers have got that booklet. If you don't have a paper booklet, you can find it online on the AHDB website. If you just search for AHDB Nutrient Guide RB209 on any search engines, you will find it quite easily. Tim, first question to you really is how much is the industry using that guide and how much do you and your colleagues use it?
It's very well used, very well respected. I think I would say it's almost universally used within the industry. And actually it's an interesting point. If you go abroad, there's a lot of countries that look in admiration at the system that we have here. So we shouldn't underestimate the value of that because there's an awful lot of work gone into it over the years. And it's a fantastic reference document. So yeah, I think it's well used. Yeah.
Well, please do continue to use that. Lots and lots of questions have come in, some of which I think Anne has already answered. They came in before you'd actually answered them, so I'm going to just try and pick out the pertinent ones. But as I would reiterate to what I said earlier, that any questions have been submitted. If we don't answer them, we will try and answer them later on for you. First of all, I'm going to start for you, Anne, specifically because Christina's had her opportunity slightly earlier. How often should organic manures produced on farm be analysed?
Well, I would say analyse them every year that you're going to apply them. I mean, that's obviously the best thing to do, so you know what you're applying each year, basically.
Good. Okay. There's been a lot of focus on arable sectors. A question for livestock here on dairy. What farming practices would be effective at reducing the carbon footprint for a dairy unit? Is that something you can shed light on here, or do you want to take that up later on?
Well, there's things like, Christina can add things in here, but there's things like looking at the diet of your animals. There's various things you can do there to try and reduce methane emissions associated with the diet. Yeah, I've got a whole list of different things that actually I could probably reply to that. Christina, have you got anything else that you could?
I'd agree with you, and yeah, so embedded feed emissions, by changing what you feed your livestock, can have a really big impact on your carbon footprint, particularly if you're sourcing feed that contains soy, because some carbon calculators consider the direct land use change of that soy production, but also manure management as well. Changing your manure management strategy will have an impact on your carbon footprint too.
Okay, thank you, Christina. I'm conscious it's 1 o'clock, but let's keep going. I think we can run for another 5 to 10 minutes, because I think it'd be a shame not to deal with some of these very useful questions that are coming in. Yeah, here's a comment. With autumn applications on heavier soils, do we not just make the loss slower? If it is not available, will it not be lost over the winter? Anne, do you want to deal with that one?
It's a balancing act, really, in terms of when you apply manures, certainly to heavy soils. Heavy soils are much more retentive in terms of nutrient leaching. They don't leach as much nitrogen, and so therefore come spring, the nitrogen that you've applied is still in the profile, and so therefore still able to be captured by the growing crop. Obviously, it depends on your overwinter rainfall. It's a balancing act, basically. Obviously, in the autumn, you've got dry soils. They're easier to, certainly with the clay and heavy soils, tracking over wet soils in the spring can cause significant damage, whereas obviously it's easier in the autumn to go on, depending on your autumn, obviously.
Okay, thank you. There's a next point here, which let's put this one to Tim. Somebody's making the point they're finding it difficult to understand slurry analysis results. Is there somewhere where we can get a simple explanation of how to interpret these? Is that something that we as an industry don't do well enough at present, or what can we do? What more could we do to help?
Hopefully the slurry analysis results should be in an understandable format. I would suggest if someone's having an issue with that to speak to the laboratory or a facts qualified advisor who should be able to interpret them for them. Yeah, I think most laboratories now provide results in quite a helpful format, so I'd be disappointed if they're not quite as clear as they should be. But,
okay, so if not, press your analyzer and make sure they're trying to give you some more help. Another lengthy comment here: to improve fertilizer use efficiency, we've got to be more meticulous with measurement and application of nitrogen fertilizers. Could the panel reflect on the value of additionally available nitrogen? Could we improve nitrogen fertilizer use efficiency by taking into account additionally available nitrogen, especially when manures or slurries or organic matter are added to the soil? Who wants to pick that one up? Anybody? Anne?
Yeah, I would agree. The additional available nitrogen, that's looking at that mineralized. So if you remember my crop, looking at crop available nitrogen, that's looking at that mineralizable fraction, that nitrogen fraction that could potentially become available over the season. So it's looking at getting a more accurate picture of your soil end supply. I would say certainly where you're using, in situations where you're using manures a lot, having an analysis, a soil analysis in spring is beneficial.
Okay, thank you.
Go
on, Tim.
I say that's an established methodology for testing the potentially available nitrogen, and like Anne said, where it's unpredictable, then it's certainly worth doing some tests, even if it's like a benchmark test, just to get a value, and then you can use that through RB209 to use the measurement method rather than the book method to come up with an SNS. So yeah.
Yeah, that's useful. Okay. What proportion of returned organic matter will end up as stable soil carbon? Anne, do you want to deal with that?
Well, obviously, I gave some figures there in terms of those sort of percentage retention are those that we've measured in long-term experiments of the carbon that's stuck around over the long term. So those are what we probably term stable carbon. They do turn over slowly, but those were the figures that I suggested would be retained. So, for example, for farmyard manure, it's around 20 to 25% of the carbon that is returned in that farmyard manure would contribute to the long-term carbon pool. It is slowly turning over still, though, but it's a long-term carbon pool.
Good. Okay. Now, you talked a bit, Anne, in your presentation about the equilibrium. Question here is, what happens to any further added carbon when you've reached equilibrium?
So when you get to equilibrium, actually, a slide that my colleague Sarah Wynne showed yesterday was really good, showing about how when you get to equilibrium, everything's in balance. So basically, the carbon that's going in, you're balancing it with carbon going out in terms of respiration. So your microbial community, your plant system is adapted to receive that amount of carbon, basically, and it will respire it off, basically.
Good. Okay, thank you. Tim, what do you know about slurry spreading? Are you able to answer a question on that?
Give it a go for sure.
Give it a go. Somebody's talking about slurry spreading here, wondering what the effectiveness of the splash plate or a dribble bar is. Do I need to invest in a dribble bar now for future preparation?
Well, certainly there's we're looking primarily at ammonia losses from application of slurries with things like splash plates. So, and I think as we move forward in terms of the way that we're monitoring in our slurry applications, I think we'll be looking at restricting the use of splash plates and encouraging the use of precision applications which try to get slurry either sort of onto or into the ground through shallow injection, which make a huge difference in terms of ammonia emissions, which is it's probably the biggest issue we face in terms of ammonia emissions is applications of organic matter. And that's the biggest way that we can improve it, through application technique, and that also has a knock-on benefits that you can use these spreaders closer to the boundaries in NVZs as well, which increases the area that you can apply slurry as well. So I would certainly encourage the use of precision application techniques for slurry as a means of it would have a knock-on effect on the nitrogen use efficiency, because you get more value of the nitrogen from the slurry, therefore you'd need to apply less inorganic nitrogen as a result.
Thank you. That's very helpful. We've got 2 or 3 minutes and then we'll draw this to conclusion. Another one for Anne. If manure is applied 1 in 5 years to tillage land, will the benefits in terms of carbon stock be lost between those applications?
No, not necessarily. I mean, obviously, your system will adapt to whatever frequency of manure application that you need. The studies that I showed were from annual applications, but actually that is rare, and actually I probably wouldn't recommend annual applications. So 1 in 3, 4 years is probably the way to go. And yes, you will, once it's hit that stable carbon pool, it will slowly turn over. So you will see it drop off, but it is a beneficial thing to do regardless.
Okay, thank you. I'm going to just finish off with a couple of questions, I think, here for Tim, in his capacity as somebody who's involved with facts and fertilizer advice. Does producing a nutrient management plan need to be signed off by a qualified fertilizer advisor?
I would certainly advise that it is signed off by a facts qualified advisor, and I think if you are in certain schemes, then that would be mandatory. But yeah, my advice would be, well, now we have farming rules for water, a nutrient management plan is effectively mandatory, and part of that should be that you're seeking facts qualified advice in order to make sure that you've got the right fertilizer plan. And I would just reinforce Anne's message that we go to a lot of trouble to produce these plans. Delivering those plans by accurate application at the right time is so important. And so I would just reinforce the fact that you've got the plan, do your utmost to apply it accurately at the right time, and that includes calibrating spreaders regularly to make sure that they're fit for purpose.
Okay, thank you. And I think we'll have to make this the last one, but again to Tim, does the use of nitrification inhibitors change the SNS index for the following crop? And does RB209 need updating to take into account nitrogen inhibitor usage?
Nitrification inhibitors generally have a act for up to about 72 days. I think that's about as long as they will work. So they wouldn't have a knock-on effect for subsequent seasons, as far as I'm aware, in terms of SNS. So they're really an in-season management tool to improve the efficiency of the nitrogen on the growing crop. So it wouldn't influence the long-term availability of nitrogen.
Okay, well, I think we must draw this to a conclusion. There are some more questions which have come in, particularly from the dairy sector. As I said earlier, Anne and Christina will be happy to take those, deal with those post the presentations this afternoon. I'm just going to draw this to a conclusion. First of all, to thank all three of our panelists, Anne Bhogal, Christina Baxter and Tim Kerr, for his helpful contributions over and above our wonderful presentations. We're very fortunate in this industry to have people with specialist knowledge and people who are willing to share that with others, and so clearly and concisely. So particularly to Anne and to Christina, thank you both so much indeed for today. Please don't forget, we have been receiving some submissions for Basis Dairy Pig Pro points. Please do contact Naya Katri at that email address. If you need to submit those, we can deal with those for you. Any further questions could also be directed to me, scott.raffle@ahdb.org.uk, and I can pass them on to Anne and Christina. And just a reminder that the recording will be made available probably towards the end of next week on our AHDB Horticulture events page, which is listed there. Now, just to finish off finally, we just want to show you a little bit more about what else is happening in our Carbon Week. So our final slide, I think, brings up the information that we need. There we are. We've had today's fertilizer webinar, but tomorrow, 3rd of March, we have carbon footprinting, save the planet and make money. Then we have another webinar on the 4th of March, that's Thursday, the ins and outs of carbon in the soil. And finally, we finish off and conclude on Friday, 5th of March, supply chain requirements, building a narrative. All three of those take place, like today, at midday, 12 noon, probably lasting for around about an hour or so. If you would like to join us and view any of those, please search on our AHDB website for those events, and you can register for free and join us for more talk about carbon and the environment. So thank you again to all our presenters. Thank you to you out there for listening and viewing us. We hope you've benefited from it, and we hope you'll find time to join us for the rest of this week. And a very good afternoon to you all. Thank you.